Okay, so say you want to remove a node from a binary search tree. This is a graphical representation of a binary search tree here. You have all of the nodes, and then these lines here are left children and right children, depending on the direction they're going in. Important thing to note about a binary search tree is all of the nodes for any given node, say 8, all of the nodes to the left of it are less than the node value, and all of the nodes to the right of it are greater than the node value. So in the case of 8, 3, 1, 6, 4, and 7 are all less than 8. 10, 14, 13 are all greater than 8. That's true for any node in the tree. So take 6, for example. All the nodes to the left of it, 4 is less than 6, and all the nodes to the right, 7 is greater than 6. Okay, so for any node in the tree, all the nodes to the left are less than it, all the nodes to the right are greater than it. And you have to preserve that balance for it to be considered a binary search tree. Okay, so say you want to remove a node from a tree. The first thing you're going to do, which I don't have written down here because I'm not going to go over how to do it, is you have to search for the node you want to remove. So if you want to remove 14, you have to find where 14 is in the tree, okay? But I'm not going to go over how to do that right now. So let's say you found 14. You know where it is in the tree. You've iterated through the tree and you've found the node. Then you have 3 cases for what's going to happen when you remove it. The first is if the node has no children. So those nodes are like 13 here, 7, 4, and 1. All these nodes have no children. The next 2 are if they have a left child or a right child or both. So examples of those are 6 here has both a left child and a right child. 3 has a left child and a right child. 10 has 1 right child. 14 has 1 left child. 8 has a left child and a right child. Okay, so those are our 3 cases, and I'm going to go over how to do each one. So the first case, if the node has no children, it's fairly simple to remove. Let's say you want to remove 1. So you take 1 and you can, the easiest way to do it in this case, and the way we have it implemented in our class, is probably to say 1's parent, which is 3. The parent of 1, remove, set its left child, which is 1, equal to null. So in that case, you would set this one to null, and now 3 doesn't have a reference to it. But there are lots of ways to remove a child directly, like remove a node directly like that. You don't have to just assign it to null. You could also just free it from memory. I'm sure there are lots of ways you can think of to remove a node. Okay. So if the node has no children, it's pretty straightforward. You just remove it. You just delete it from the tree. Okay. And one way to do that is assigning it to null. And assigning so just assigning it to null is one way to do that. Okay. In the next 2 cases, it gets a little bit more complicated. So in these cases, it means a child exists. So you would say if a left child exists or if a right child exists. And just because of the way this tree is laid out, I'm going to start with the 3rd case here, if the right child exists. So you say if the node has no children, and if it does have a child, then you move on to these cases. So we're going to say if the right child exists. So let's take 3 here. We want to delete 3, okay? And we're going to say if the right child exists, which it does, it has a right child in 6, The first thing to know about both of these cases is that if you were to do it like you did in the first case and just set this one equal to null, that breaks the tree, right? Because as you can see, if there's null here, it's gonna, this tree doesn't, this subtree now on the bottom, 1, 6, 4, and 7, all of those nodes are no longer part of the tree because for all intents and purposes, you can consider null to just be a blank space. So this tree is broken now. So you can't just delete it, right? You have to somehow reassign these nodes to the rest of the tree. How do you do that? Well, you would take one of 3's children and put it there in place of 3. So we're going to say that in this case, we're taking one of the right children of 3 and swapping it in place of 3. So let's just say that, let's do the most straightforward way to do it first. Let's say we move 3 out of there, we dereference it, and we change it to the 6 node. Well, as you can see here, so the way you would write this in code is like 8's child no longer is 3. 8's left child is no longer 3, it's 6. And so 6 would still have 4 and 7 as its children, and 1 would now be hanging somewhere else. So obviously that doesn't work because or let's just take it to be like this since we can see it like this right now. So if you just were to move 6 in where 3 was, 6 has 1 as a child, which is fine, but now 4 and 7 are hanging to the left of it. And even if these were connected to it, let's just say somehow these were still connected, 4 is now to the right of 6, which we know that breaks how a binary search tree works. We can't have that. You can't have a node that is less than another node to the right of it. So this doesn't work. Just swapping in 6 doesn't work. We have to swap in some number. We have to swap in one of these nodes that's to the right. So out of 6, 4, and 7, then it turns out that the node we want to swap in for 3 here is 4. So we want to take 4. We want to take 4. We want to move that here. And as you can see, if we put 4 here, this is totally fine. This works as a tree. You have all the nodes to the left of 8 as less than it, 4, 1, 6, and 7. And in the case of 4, all the nodes to the left, 1, and all the nodes to the right, 6 and 7, are respectively less than and greater than it. Okay, so the question becomes, how do we find 4? How do we decide 4 is the right node to swap in here? Well, what you do is, if you're on the right, if you're going down the right tree, if the right child exists, you move down, you find the right child once, so you go from 3 to 6 down the right tree, and then subsequently you go down the left tree. You keep going left. So go right once and then left. Okay, and that'll find the next closest node. So you can see 4 is 1 away from 3. Okay, I'm going to do another example to demonstrate this a little bit better. So let's say you want to go down the left side of the tree. Let's say you want to remove 8. Okay, so if you want to remove 8, in this case, we're going down the left side. So you're going to go down left once, and then you're going to go down right and right. So you're going to go down left once, and then keep going down the right side of the tree. So left once, 3, right, 6, right again, 7. You take 7, you reassign it to where 8 was, and as you can see here, all of the tree is still a binary search tree. All the nodes to the left are less than 7. All the nodes to the right are greater than 7. let's say instead you went down the right side. So you would go, so you remove 8, right? And then you go down the right side once, and then you go down the left trees. You went down the right side once, and then 10 has no left node. So you just take 10, you reassign it to here. 10's nodes are still connected to it. So 14 still has a reference to 10 as its parent. So this all works fine. And now the tree looks like this. And this is still fine. 14 and 13 are both greater than 10, and all of these nodes to the left of 10 are all less than it. And then you would just free this memory here that 8 is stored in. That would remove it. Okay, so hopefully that helps a little bit understand how you remove a node from a binary search tree. Let me know if you have any questions.